Let's take a look at the area between two curves. So this is an interesting idea. You could have some graph and you have, two different curves. You could be doing all kinds of different things. And, you might be looking for, say, this particular area between the two curves. And we'll call this one, say, curve A, and the bottom, this other one, curve B. Okay, so how do we get the area between A and B? Now, what we've explored so far is that you get the area of curve A by just taking the integral of everything underneath the curve. Same thing with B. Now, B underneath the curve is here, right? Let's just look at it from this point, okay? And the idea is this. If we take the area of A underneath the curve, when we subtract the area of B underneath the curve, we will get the area in the middle, the blue part. Now, one other thing that we would need is this point of intersection and this point of intersection, okay? Because, we're not looking at necessarily the whole curve here, right? And sometimes you actually have to find the actual point of intersection. So to find the area between the two, it's going to be A minus B, but then we need to find those individual points. Now, we're going to have, right, like let's call this one maybe x1, y1, and this one x2, y2. And what's critical with area is you have to think like, what's your differential? Is it like a dx or a dy? And you think about like, what is your average cross section? Meaning like, what's your average rectangle? Your average rectangle is like one of these guys right in the middle. And certainly it has a sort of a dx. And so the idea then is you are going to be integrated with respect to x. So in this case, you would go from x1 to x2, and everything would be in terms of dx. Okay, so that's just a general example of how you would get the area between two curves. Okay, so let's make it practical. Let's do a practical example. Okay, so how about the following example, and let's do it with a visual here again. Okay, so we're going to look at the area between, let's say, y equals x squared and y equals x. Okay, so we've got y equals x here at the top and y equals x squared at the bottom. And, it might depend on whether you know the point of intersection or not. Sometimes you need to find it out on your own. Sometimes it'll be given to you. Okay, I think in this particular case, we can find them out. So again, the goal is to find this area here. Okay, so we just take the upper integral to y equals x and we subtract the lower integral y equals x squared. So let's set that up. So it's simply the integral of x minus x squared. It all is dx. And we're evaluating this between what? Well, what are these points for x? It's 0 and 1. The reason why I know I want my x and not my y, although they're the same here, 0, 0, and 1, 1, is because, again, I'm having vertical rectangles. Okay, so this is between 0 and 1. And we can evaluate this straight out now. So we get x squared over 2 minus x cubed over 3, evaluated at 1 and 0. Sorry, it should be a 3 here. And the zeros will be gone, and then we get 1/2 minus 1/3. And common denominator is 6. That's like 3/6 minus 2/6, so this in fact equals 1/6. Okay, so the area under this curve is 1/6. All right, let's do another example and see if we can get the hang of it. Okay, for this next example, let's consider, let's do sine and cosine. Okay, so we're just going to look at the first quadrant. And, if the sine curve, we're just going to take a portion of it, like where they intersect. So sine starts up and goes like this, and cosine starts, it's hard to draw these symmetrically, but cosine starts up and goes down like this. Okay, and what we're just going to be looking for is this actually right here in the middle. Okay, and so we've got, excuse my art here, math art, y equals sine x, and y equals cosine x. Sorry, my cosine x, you know, I don't know, it's not looking good, or just leave it. Okay, y equals cosine of x. Okay, so why does it look good? Because it doesn't curve that way yet, right? It should be going down. And you know, let me just maybe fix it a little. All right. I'm just gonna erase that part of it. Okay. So to get the area, once again, we've got vertical rectangles, and we're gonna take the top one, the sine of x, minus bottom curve, cosine of, oh, sorry, the top curve is, it's written up there, but the top curve is clearly cosine of x, right? Yeah, so, and this actually brings up a very interesting point. We'll talk a little bit more about it, but it's the point is, what if you get it wrong? If you get it wrong, like, look here, it's gonna be reversed, and you get like negative 1/6, but area is always positive, so it's okay. You can just make it positive. Area is, in fact, the absolute value. Okay. All right, so cosine of x minus sine of x dx. And what are we evaluating from? What points? So we're just looking at the first quadrant, and we're just going up to their point of intersection. And so this is from 0 to, okay, well, what's their point of intersection? The point of intersection is actually, you know, where they're equal. So where is sine x equal to cosine x? If you know your trig, you know that's actually at pi over 4. Okay? Both root 2 at pi over 4. Okay, so we do our integration. Take the first term first. Integral of cosine is sine. And integral of sine is negative cosine, so it's going to be plus cosine of x. And we evaluate these at pi over 4 and 0. Okay, so at pi over 4, we already said we get the root 2 over 2's. And so that's root 2 over 2 plus root 2 over 2. And then we've got to subtract at 0. It's not just 0, right? Sine of x is 0, but cosine of 0 is 1. Okay? Now, let's simplify this a little bit. So if you add these up, right, you've got 1 root 2 over 2 plus 1 root 2 over 2. That's 2 root 2 over 2. Right? Which is just root 2. And so here, right now, so it's 2 root 2, because you've got, you know, one of them. You've got two of them. Get 2 root 2's, and that's actually just root 2 minus 1. And root 2 is about 1.4, and so that is actually greater than 0. Okay, so pretty cool. Let's do another one, and for this next example, let's consider the following. Now, in some cases, you might just be given the equations, and you might need to even graph it on your own. Okay, and so let's try this. We're going to try, we'll keep it still relatively simple. We're going to take area between x equals, let's do x equals y squared, okay? And let's do how about this? We'll do x equals y squared minus 2. And then y equals x. And whenever it says area between, it's sort of like in these examples, right? You're looking at just the area between them. Okay, so if that's the given problem, what do you do? Well, the first thing you do is make a graph, because you want to see, it's important to see, okay? Even though, like, with the absolute value, you could just take one minus the other, there's some other subtleties that we have to look at. Okay, so let's start with the, I guess, the first one. So bigger. Okay. X equals y squared minus 2. So y squared is like a parabola like that, but if it's minus 2, and when y is 0, x is -2, and so it's gonna go out like this. Okay, so that's what the parabola looks like. And then y equals x, we know it just goes like this. Okay? So what we need to do is find these points of intersection. Okay, that's the first thing, because when you're doing an integral with area, you've got to have them. And so how do we get those? You get those by solving the equation, right? Like in some cases, like you might just know it, might be obvious, not so in this case. And so what we're going to do is we're going to solve these. Now, what you want to do here is actually solve for y, because the x's, it would be difficult to solve this one for y. What I mean is they're both saying what x equals, so let's set them both equal to each other. And we can plug in the y here, and we get basically y equals y squared minus 2. Okay, so this is a quadratic, so we've got to treat it as such. So we get 0 equals y squared minus y minus 2. Now, does this factor, we can check, are there two numbers that multiply to give us -2 that give us -1? I think there are, right? It looks like we would have, can keep the 0 in there, y minus 2 and y plus 1. Okay, and so the points of intersection are going to be when y equals 2 and y equals -1. Okay, and so clearly this is going to be 2 and this one is going to be -1. Okay, that's good. Now, what about x? Well, let's think about what our cross section should look like. And when I say cross section, like these are all vertical. Now, look at this one carefully. If I go vertical, it looks good, it seems fine, right? But what about when you get beyond that point? Uh-oh, this is trouble, okay? Vertical lines that go from, it's not going from the one curve to the other. That's a problem, okay? Because it's not that you can't do it, but it's let me just put it like this. If you switch it and say, you know what? Maybe I should go this way, because now it's always the one curve minus the other. That's what you want to do, okay? And when you do that, right, your cross section becomes horizontal, and so your differential is now a dy, not a dx. And what that means is you want everything in terms of y. And this is like a good thing here because we've got them in terms of y, at least this one. And solving that one for y, not fun. Okay, so let's set up the integral and see what we would get here. Okay. Where did I put my white marker? That's a little funny. Oh my gosh. I don't actually see it, so let's go with the green. Be a fill off. Okay, so to set up this integral, we're going from what? Well, we're going from the y, so it's from -1 to 2. And it is the one now to the right, right? It's not a top bottom, you're going right to left, right? Because you're, you know, the positive is to the top. Well, for y, positive, I mean, it's not really y, positive's to the right, right? Like your x. And so that one is just y. So it's going to be y minus the other one, which is y squared minus 2. Use parentheses. And the reason why I say this is because if you don't, you'll miss that that should be a +2. And importantly, this is all dy. Okay? So now we can just straight out integrate it. We get y squared over 2 minus y cubed over 3 plus 2, evaluated at 2 and -1. Okay, so let's just finish this one out. We get 2 squared is 4 over 2 is 2, minus 8/3, that's the 2. And we got the plus 2 here. Now, when you do these minuses, you've got to be careful when you plug in negatives. Okay, I'm just going to try it. It can be, you know what, I'm going to do the careful thing. The careful thing is to use parentheses. Because you plug in a -1, you get 1/2. Now you plug in a -1, you would get negative 1/3, but that makes it positive, and this is what I mean about the trickiness with the sign, because you're going from like a negative 1/3 to a positive 1/3, but then if you have this negative there, it's got to be back to negative. And then same with this +2 becomes a negative, right? Wait, I didn't integrate that. Oh my gosh, total mistake. Happens, right? So I caught that because they cancel each other out, and certainly it's +2, but it should be +2y. Okay, because the constants cancel out, but this is not really a constant. And so that becomes 2 times 2, which is 4. And this one becomes 2 times -1, which is -2. Okay, so what is this when we add it all up? I mean, it's kind of a pain. Like, let's just do maybe the 2 + 4 is 6. That becomes a +2, that's 8. So I get an 8, and then what's the rest of it? Well, I've got to, to get the common denominator, it'd have to be 6. And so if I double it, I get -16. Oh, this is kind of a pain, isn't it? -16 -3 -19 +2. Am I doing this right? -17 over 6. And so that's going to be 48 -17. I believe that is 31/6. That's what I'm getting, is 31/6. Okay, so let's just do a recap. To find the area between two curves, okay, what you do is you typically take the top curve or the right curve minus the lower or the left, right? We looked at a couple of basic examples. To do it, you've got to find your points of intersection. This was 0, 0, 1, 1. This one we had to solve for it. Then, after you have it set up, you just finish it out by computing a regular integral. But you must be careful. You must be clear that in your visual, okay, everything lines up perfectly. In this one, it did not, because we got to this part that was shaded in right here white, and like it was just the same curve minus itself, and it doesn't work that way. It's got to be the one curve minus the other. And so in this particular example, we had to rotate our orientation to be in terms of dy. And how do I know it's dy, which is which? Because it's what your tiny part is, right? The length, the whole thing, in this case, is just one curve minus the other, but it's an integral, and when you integrate, it's a bunch of small rectangles. It's a bunch of Riemann sums in effect. And so that's your sort of your height of the rectangle, but your width now is dy, and in all these other examples, the width was dx. So watch for that very carefully, and it's good practice to even practice watching for it carefully when you're doing integrals, because it becomes even a little bit of a bigger deal later when you see volume.